let us begin talking about graphs. Right on time, Robert. There you go. Still getting used to the new they are, but I can make you write all this out. You crazy, man?
Nice, I like this.
How much space do I have? Oh,
What I would recommend you do, when I give you something like this is more like a workbook. I would recommend a highlighter or pencil or pen and just sort of, make little notes on the side as we go. That's what I recommend you do. All right. So we're going to talk about graphs. Now, I know you guys know lots about graphs, probably done lots of graphs, read graphs, made graphs, all that kind of stuff. I just want to sort of review, get you back into the swing of things a little bit, and do a little bit of physics along the way. So a well-designed graph is more than a picture with 1,000 words. It can give you more information than either words, columns, numbers, or equations. To be useful, however, a graph has to be drawn properly. In this section, we will develop the use of graphs to display data. So, graphing data. One of the most important skills to learn in driving cars is how to stop it safely. How many people have completed their driver's ed? Congratulations. Did they teach you anything about braking distance?
Nope.
Yes, yes.
Did you miss that day, Katie?
Possibly. I missed a couple.
Remind me not to drive with Katie. What did they teach you about driver's the braking distance?
Braking distance is longer when you're going fast.
Okay, it is longer. How come?
Never mind, I was there for that class.
It does have more momentum, that's true. Do you know anything about if you go twice as fast, how much longer you have to stop? No?
More than twice.
Twice and then some.
Twice and then some. So you didn't hear that class just saying.
No,
Our teacher didn't really teach taught us.
Okay, well, we'll talk about that today. There's the braking distance. Now, there's also another
reaction
distance.
time.
That's the time, right? What's the reaction time, right? Like, what does that define as?
The time where you see an obstacle and the time you react to it.
Okay, so the time you're driving down the highway, you see a deer or something other, right? Your brain goes, oh, I should probably stop.
And then you hit brake.
And then, yeah, so it's the time that your brain goes, oh, it must stop, and your foot actually gets to the brake, right? What would be like sort of average reaction time, like an actual number? How much? 4 seconds to get your foot from the gas to the brake? Don't ride with her, you guys. 0.5. 0.25? You see something? 0.1?
That's a huge lynching case. That's taking 10 seconds. That's like a point.
Okay. All right. So maybe, what did you say, Mary? 0.25?
I did.
You said 0.25. I'm thinking maybe 0.25 if you're like this. You're like, right. Right? Most people don't drive it. Right? Yeah, maybe about that, right? Maybe like, ooh, I should stop. Right? Okay, so we're going to go through all the physics of that. All right. No car can stop on a dime. The faster the car is going, the farther it travels before it stops. If you study for a driver's license, you probably found a table in the manual showing how far a car moves beyond the point at which the driver makes a decision to stop. One manual shows that a car travels a certain distance between the time the driver decides to stop the car and the time the brakes are applied. This is called, as Brett mentioned, the reaction distance. Okay, so we talked about reaction time, I guess, really. What's the reaction distance during the reaction time? The distance you travel during the reaction time. Now, obviously, if you're going faster, right, if Kish is speeding along at 130, he's going to go farther, even though his reaction time is the same as somebody else, right? Okay. When the brakes are applied, the car slows down and travels the braking distance. So the braking distance is the actual distance when you're actually stopping, right? Okay. So table 1 in the bar graph, figure 1, show these distances together with the total stopping distance for various speeds. Now, in physics, we tend to deal with meters per second. Of course, everyone knows how long a meter is, right? It's a big stick, so meter per second. So 10 meters per second, 10 of these guys, right? So how far is 10 meters roughly? Almost the width of the crossroom?
Like to here.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, it should be 10 to that wall.
10 to the wall. Roughly, right? Okay, so that distance there in 1 second, how fast do you think that is in kilometers per hour?
0.01 kilometers per second. 5 per second.
I want to know in kilometers per hour.
Okay, so
Like your speedometer. What would your speedometer read if you were traveling from there to there in a second? 100?
No, maybe like 10.
10.
I don't know.
20. We're just guessing.
Yes, I can tell by the wide range. I can tell. Does anyone remember the magic number of 3.6?
Oh, it's 3.6, right?
You remember the magic number, right?
Is it 3.6?
3.6.
I am.
Do you know where the magic number comes from, Ben? Do you remember?
Oh, it's something like the minor.
Seconds in a minute?
Yeah, that one.
Right. 60. Minutes in an hour?
60.
60. 60 times 60, Connor?
3,600.
Very good. 3,600. Divide that by 1,000, because there's 1,000 meters in a kilometer, and you get 3.6. Magic number. So what I need you to do is I need you to complete this column right here. Take 10, 15, 20, 25, and 30, multiply by 3.6, and tell me what the speed in kilometers per hour is. So 10 meters per second actually is only
36.
36 kilometers an hour, which would be about how fast you should be driving maybe on like a residential street, right? Yeah. You better not be driving any faster on my residential street, or I'll be putting pieces of 2x4 with nails on the street. Well, I understand that. That doesn't mean you have to drive that fast. You drive at the appropriate safe. No, maybe 36 is a bit slow, but certainly if you're driving down a narrow residential street with cars on both sides, you shouldn't be doing it. Right. Now, the next one, 15, I think, is about what, 54, is it?
Yeah.
Okay, so 54. Would you get pulled over for doing 54, say, on that road? No. That's an appropriate speed for, say, mountain or river or main street. Perhaps. Gage, we've had this discussion before. Just remember where you are. 20 meters per second is 72. So like, you know, like going out of town, right? Eclipse kind of thing.
Can we start a petition to get a 70 kilometer per hour sign by the ACC when you're going towards KFC? Because that's actually 70 zone.
There is a sign.
Just because it says 70 doesn't mean you have to go 70.
Yeah, but did you put that on the highway below 40?
You'll never, sorry, you cannot force people to drive faster.
No, there's not a sign.
There is a sign.
Not when you
Really?
when you turn.
Oh, there used to be.
Yeah, but there's not one now.
Oh.
I got it.
Wow, you're
No, I just.
all right. No, I meant for your crime. 25 is how much?
90.
And is it 108,000? Okay. So yeah, when you're driving down the highway at 108, like people are apt to do, 30 meters per second. So that would be like the length of that hallway from the windows right down to the stairs in a second. That's a long ways, right? It's a long, long ways. Yeah, that's how fast you're going. Okay, so now let's talk about reaction distance and braking time. Okay, now look at those two columns. Tristan, can you tell me what would the graph of reaction distance look like? Like, what would be the shape of the graph? All squiggly and junk, says Logan. Can you be a little more precise? I'll give you a couple options. Would it be straight or would it be curved? It'd be curved. What do you think, Connor? Is he right? Would it be curved? You think it's straight? Why would it be a pattern, you think? When you say a pattern, you mean a linear pattern. Because you can have a curved pattern, right? Okay.
It's going up by 8.
You don't think it's a curve?
Basically, we're on the same interval. Yeah.
Are those kind of the same interval?
It's the same road.
Okay, so like from 7.4, let's say 7.5 to 11 is like about 3.5, right? That's about 3.5. Is that about 3.5? Pretty close. Is that about 3.5? Yeah, a little bit more maybe. They all seem to be going up by a little bit more than 3.5, right? So I think Connor might be right. I think it might be a straight line. Tough to say without actually doing it though, right? What about the next one, Connor? Would that be a straight line or would that be curved?
Because it's going up in different numbers.
Each interval seems to be bigger and bigger, right? Okay, so you got a general idea, but to actually figure it out, you have to actually look at it. You got to do a little bit of calculating and estimating, right? It'd be a whole lot better if it was just a graph, right? The point of what I'm saying is that graphs can be very useful. Yes, I know there's a graph right there. Okay, so we've converted the speeds. The first step in analyzing data is to look at them carefully. Which variable did the experimenter or the driver change? In our example, it was the speed of the car. Thus, speed is the independent variable. The independent variable. Where's my highlighter? The independent variable. Okay? You've probably heard about independent, dependent variables, right?
Yes.
Okay. So the one that is changed in the experiment is the independent. The other two variables, reaction distance and braking distance, changed as a result of the change in speed. These quantities are called dependent variables or responding variables. Dependent variables. Now, does anyone remember where independent and dependent go on a graph? Which one goes on the X? Independent goes on the X.
Like goes along the
Yeah, along the X, along the bottom, right? And the dependent one is obviously then the Y, right? There are very rare occasions when I switch them. It's usually because of the dependent one is usually the one that you actually measure, right? Like in this case here, we would have had someone driving at 36 kilometers an hour, and then we would have checked to see how long it took them to brake, right? Okay? And we would have a graph that would look kind of like this. We would have distance here and speed here because we measured the distance. But sometimes the one that you want to measure is hard to measure. There's an example of that in the next month or so. So sometimes I say, even though we're measuring the distance, or sorry, even though we're measuring the time, I want time along the X. So there is a couple of occasions when I do a switcheroo. Okay? But for the most part, independent should be on the X. Okay, so how do the distances change for a given change in speed? Notice that reaction distance increases by about the same amount, as Connor noted, for each increase in speed. The braking distance, however, increases much more as the speed increases. The relationship between the distances and speed can be seen more easily if the data are plotted on a graph. To avoid confusion, we should plot two graphs, one of reaction distance and the other of braking distance, which I conveniently have done for you. You know what I probably should do? Because Logan says he hates it when this happens. I should probably leave a blank graph there and have his graphic, shouldn't I? No. Next time. Okay, so on the graph, the bottom one is which one? What's the bottom graph?
Oh,
it's the reaction distance, right? It's the reaction. And what shape is it?
Diamond.
Not the shape of that dot, the shape of the line. It's a line, right? It's a straight line. It's not very steep though, right? It's a straight line. Now the middle one here, the squares, is the braking distance, and you can clearly see that it's a curve. What's the third one, Matt?
Total distance.
Total distance. And how did I come up with total distance?
The total distance, the reaction rate.
Yeah, I added the two together. Is it surprising that it would be a curve? Right? If you add a line and a curve, you just basically all you're doing is just taking the curve and doing what?
Lengthening it.
Just moving it up a spot, right? Moving it up that height. Yeah. Okay, and it's obviously a curve as well. All right. Okay, now, what is the starting point for the x here on the graph? Sam, what's the starting point for the x? 10 meters per second, right? Yeah, 10 meters per second. What's the starting point for the y? Not around, it's exactly 0, isn't it? Yeah, okay. So is that common that you're going to start at 0 for the y and 10 for the x, do you think?
Yeah.
Yeah? Yeah. It should probably be 0 and 0, right? Excel does a lousy job at this kind of stuff, and it should probably be at 0, 0. We're going to talk about that right away, but I just wanted to point that out there for you. But that's probably not the best kind of graph. Okay, so how do we plot graphs? And you guys know this. Again, this is just review. So identify the independent and dependent variables. In other words, ask your teacher which one goes on the X. Don't do that, figure it out for yourself. The independent variable is plotted on the horizontal or X axis. The dependent variable is plotted on the vertical or Y axis. In our example, speed is plotted on X and distance is plotted on the Y. Determine the range of the independent variable. Who happened to pick on you? Ray, let's pick on you. What's the range mean?
Like distance between points.
Which 2 points?
The starting and the first.
Not the same point, is it?
The starting in the first one, the sides.
Isn't the first and the last?
I think did you mean the first and last? That's what you were trying to say? Okay, good. Okay, it's the distance between the first one and the last one. What's range and domain mean in math class? Aurora, what's range and domain mean in math? Remember?
I had to math a long time.
Oh, okay.
Those things, the left X, the right X.
Domain is the x's?
Yeah, like the point to the left. Range points to the right.
It's
X
height.
Yeah, you're right. Which one's x?
X is horizontal.
Yeah, but is it the range or domain?
Range. Domain.
Domain is the x, right? Yeah. In math, they use the word domain for the range of the x's, and they use the word range for the range of the y's. We're just going to say range. Okay, range just means top to bottom. Okay. So determine the range of the independent variable plotted. In our example, data are given for speeds between 10 and 30. If I go back to my data, what's my first speed? 10. What's my top speed? 30. I got to make a graph between 10 and 30. Now, should I include 0?
Yeah.
How come not?
You always need the original order.
Well, do you always need it? It's certainly better if it does, right? Did you have something to add, Rebecca?
Oh, I was going to say you shouldn't always include it because sometimes you're not starting with 0.
Well, that's true. You should probably decide if 0, 0 makes sense in the situation, right?
Depending on.
It depends on what you're graphing. But if you can, try to include 0. That's what I'm getting, right? Okay? So I'm going from 10 to 30. I can easily get 0 on there. Let's use 0. What if the independent started at 1,000 and went to 1,020? Would you try to put 0 in there? No, because you're going to have like all this graph way over here and you're going to have 0, right? Doesn't make any sense. Yeah, you can do the squiggly line. Right? You can do the squiggly line, you're right. Okay. Decide if the origin 0, 0 is a valid data point. In other words, even if the data doesn't give you that, would it make sense to? So let's go back to our data. If you're driving a car and your speed is 0, would you have a reaction distance of 0?
Yeah.
You're sitting there in your car, you're in park, what's the reaction distance? 0, you're already stopped. Absolutely, 0, 0 is completely valid. Should you include it in your graph? Yeah, we should. Okay, so 0, 0 should be on there, even if it's not part of your data set. When the speed is 0, reaction and stopping distances are obviously both 0. In this case, then your graph should include the origin. Now, spread out the data as much as possible. There's some of you that love to save paper, right? I give you a big sheet of graph paper, and they squeeze the graph into 1 square centimeter in the down left-hand corner. I'm saving paper. I'm going to use this later. No, you're not. You can't even put it in the rings. Okay? Put it on the paper so I can see it, please. Let each space on the graph paper stand for a convenient unit. Please don't ask me how much each space is worth. You decide. You're in grade 11 now. 10, 2, 5, 10 spaces is good. Number and label a horizontal axis, and then rinse and repeat for the y variable. Right? Do exactly the same thing for the y. Plot your data points on the graph. Draw the best straight line or smooth curve that passes through as many data points as possible. Do not use a series of straight line segments that connect the dots. Do not connect the dots. Why not? Do not connect the dots. Why?
Because there's no constant change.
Well, most experiments, do they give you nice, beautiful straight lines? Some that I'm going to give you are, right? They're going to be like, incredibly made up kind of thing. But most of the time, your graph's going to look kind of something like this, right? Now, should you take those and go like this? Is that a good graph?
Yeah.
With those noises, it's a terrible graph. Doesn't tell you anything. Okay? Does this mean that when the x is somewhere between those two, that's where the y is? I don't think so. What should you have drawn?
Line of best.
A line of best fit, exactly. A line of best fit. What happens if it's a curve? Draw a curve of best fit, right? Draw a curve of best fit. Is Ben's line of best fit going to be exactly the same as Tony's line of best fit? No. Is that okay? Perfectly all right. They have different opinions of what it's going to look like, okay? The point is that it's the process that's important, not the exact number. Okay? Do not connect the dots. Get a ruler, draw the line of best fit, or curve best fit. And give the graph a title that clearly tells what the graph represents. Okay. Let's talk about the different kinds of relationships. Mathematical relationships. We got linear, we got quadratic, and we got inverse. Let's start with linear. It's pretty easy. Linear relationship, the graph is a straight line. The graph figure 2 of reaction distance versus speed is a straight line. That is, the dependent variable varies linearly with the independent variable. There is a linear relationship between the two variables. What a linear relationship means, the graph's a straight line, but what does it mean about the data kind of thing? Like if I go up by,
It's constant.
if I double one, then the other one should
Double.
double, right? That's a linear kind of relationship. Do you all remember what y equals mx plus b?
Yes.
Is y equals mx plus b universal across the globe?
Yes.
No. I guess.
I'm asking. Mx plus b?
Yeah.
Yeah? You're not convincing me. Y equals mx plus b. What does the m stand for? Slope. What does that mean, Rebecca? Oh, you just isn't. Yeah, rise over run. How steep the line is, right? The m is the slope. How steep it is. What's the b?
The line of wire.
And what does that mean?
Constant.
Where the line crosses the y-axis.
Crosses the y-axis, right?
Yeah.
The y-axis. So we're talking about, like in this graph down here, the slope is how steep it is, the rise over the run. The b, the y-intercept, is this point right here, right?
Yeah.
And well, not technically because that's actually starting at 10, isn't it? Right? Yeah. It's this point right here. If this is 0, 0, it'd be like that, right? If that's 0, then this point right here is called the y-intercept. What's the x value? Let me see here. Load that. Yes. What's the x value at the y-intercept?
That's
The value of the x at the y-intercept. It's surprisingly easy. What's the x value? The value of the x coordinate. And don't listen to Ben. It's not 4. Ben, it's a bit. Sam, help me out. What's the x value at the y-intercept?
0.
0 is right. It has to be, right? Because at the y-axis, what's the x value? Y-axis means, right? 0. Okay. Each constant can be found from the graph. The slope m is the ratio of the vertical change to the horizontal change. Fancy words for rise over run. To find the slope, select 2 points A and B as far apart as possible on the line. Do you want them like right beside one another? Yeah, it's probably not the best. Do they have to be exactly on the line? Yeah, they kind of do, right? Like if I'm finding the slope of that black line, should I use that point and that point?
No.
That's going to be the slope of that line. Don't do that, right? Don't do that. Okay? Use slopes that are, use points that are on the line. You could use that point, maybe that one, or pick points that are right on the line. Okay? Is your slope, Matt, going to be exactly the same as Katie's?
No.
Is that okay?
Yeah.
They might be because you guys might be working together.
But
But
she cheat off me, so.
nah, she would.
It's about that.
I do that enough.
It's okay if they're not exactly the same. I'm probably going to give you the answers. If my answer is 0.2 and you get 0.18, are you going to come to me and say, is that close enough?
Yes.
Don't. It's close enough. Use your judgment. Okay.
Have good judgment.
So let's look at the slope of this line right here. Now I've selected 2 points. I've used, that happens to be, it looks like I've used this point and this point here. Okay? You might want to jot these numbers down. Okay. So what's the x and y coordinates for this point right here? Well, the x is clearly 10. and the y it looks to be like somewhere between 5 and 10. I can see over here it's 7.4. Okay? So those are the x and y coordinates for that point there. These x and y coordinates are 25 and looks like 18.5. Okay, so those are my points. 10 and 7.4, 25 and 18.5. How do I find the slope here now? Right? Do you always take the one on the right first? Take the 18.5 first?
That's right.
Yeah. Okay, so it's going to be 18.5 minus 7.4, and you can see that right here, giving me a rise of 11.1. The run is from 10 to 25, so it's 25 minus 10, which is a run of 15, giving me a slope of 0.74. 0.74, Rebecca.
Does it not matter which one you pick first in terms of precision?
Yeah.
Okay.
Yeah. You'll notice that it's 0.74 s. What does the s stand for, Bo? Seconds. Where did the seconds come from? Have you ever heard Mr. Friesen talk about dimensional analysis?
No, never.
I never had this.
Never tried.
No? One student actually thought he was saying delusional analysis. It's kind of ironic there because I think they were suffering from delusions. But anyways, so we've got meters divided by meters per second, right? Meters divided by meters per second. Who can tell me how to divide fractions? What's the rule? Hand went up and the right back down.
Well, I don't know how to do that.
Oh.
I don't
Who knows how to divide fractions?
That's what I was doing.
Robert or McMurray? Divide fractions. What's the rule? Cancel out the what? Can you always? You guys are making it too complicated. I've got 1/2 divided by 3/4.
You find the reciprocal, don't you?
In English, what does that mean?
Multiply reciprocals.
It's funny to-
Flip it, right?
That's English.
I know. Good English. You flip the second one, find the reciprocal, very good, and multiply. Okay, so what I mean is I'm going to take meters and divide it by meters per second, which means meters times seconds over meters, and what happens to the meters? They only cancel when you got one on the top and the bottom, right, Mary? That's what I was concerned. You can't just, oh, well, there's m's, I'm just going to cancel. They got to be top and bottom, though, right? Okay, so I end up with seconds, okay? So the 0.74 is a time. How do I know it's time?
It's a
It's seconds. So what time is it? And don't say it's whatever clock it is. Is it?
174 seconds.
What time is that? What does that represent? 0.74 seconds?
Oh, takes you out that slope.
Bingo. The reaction time.
How do you know
The
that?
reaction time is 0.74 seconds. This
Oh.
person takes 0.74 seconds, or took 0.74 seconds to get their foot from gas to brake. Does that seem like a reasonable amount?
Yeah.
I think it is. Why is it a straight line? Because they have the same reaction time in every instance, right? Now, is that 100% true? Like, you can have exactly the same reaction time every time?
Yeah.
No. So that line's not going to be perfectly straight. It's going to be a little bit jagged, but more or less straight gauge.
Well, if you're driving a standard, you also have that
Yes.
time, how long it takes to push it off the clutch as well.
Because that takes more time.
Smart out, though.
Because that happened to me.
Yeah?
Now there was a donkey that ran in front of me. I was
A
driving,
donkey?
I was driving a grain truck.
Yeah.
So,
Notice that the units have been kept with the variables. Now, in this point here, the y-intercept b is the point at which the line crosses the y-axis, and is the y value when the value of x is 0. In this case, when x is 0, so is y. And so for special cases like this, when the y-intercept equals 0, the equation just becomes y equals mx, the b goes away. The quantity y varies directly with x. After drawing the graph and obtaining the equation, check to see if the results make sense. The slope indicates that the increased reaction distance for an increase in speed. It has units of meters per second, just seconds. Thus, it is the time, the reaction time. It is the time your body takes from the instant it commences to stop the car, registers in your brain until your foot hits the brake pedal. Thus, the slope is a property of the system that the graph describes. Now, what do I mean by that? It means that the slope has a meaning. The slope has a meaning. In this case, the slope refers to the reaction time. Every slope has a meaning unless it's made up numbers. Okay? I will be expecting you to be able to come up with the meaning of the slope. I haven't given you that skill yet, but I'm just giving you some warning here.
No, in English.
Okay? We'll get to it. Okay? I'm just giving you some warning here. Right? In this case, though, the slope is reaction time.
Yay.
Okay? The value of y does not always increase with increasing x. If y gets smaller as x gets larger, then the slope is less than 0 and the slope is negative, right? You guys know that.
Yep.
All right. Quadratic relationship. What does that mean? Anybody know what a quadratic equation is? Miguel, I haven't picked on you yet. Quadratic equation. Got a clue? Zachary? I'm using it for whacking. No, that's not what I thought.
Are you kidding me?
I would never kid with you. Hang on.
Go ask me.
Okay. Quadratic relationship, anybody? Quadratic equation? How do you know what quadratic is? Not? No? You think so, but it's actually an x squared. X squared. Anything with an x squared in it. Do you know what a parabola is?
Yeah. It's a smiley face.
The smiley face thing? It's like a curve like this, right? Looks like a salad bowl. Oh, it's not a smiley face. Oh, okay, maybe the smile. Okay. So figure 4, distance versus speed is not a straight line, but rather looks like a parabola. Actually, just the right side. This indicates the braking distance varies as the square of the original speed. Oh, now what the heck does that mean? I'll get to that in a second. In other words, if you double your speed, the braking distance increases 4 times. Whoa! 2 and a little bit. If you double your speed, the braking distance increases 4 times. How did I get the number 4? 2 squared. Okay? Now, what does that mean? Let me just read this here. No, I'll come back to that. If it takes a person 40 meters to stop after driving 50 kilometers an hour, how far will it take to stop if driving 100? Double the speed. Connor says 80. Easy, right?
I don't know.
Just 80 kilometers, right?
No,
Who agrees with Connor?
80 meters.
Oh, yeah, not 80 kilometers. Thanks. I'll read the question again. If it takes 40 meters to stop if you're driving 50, how far does it take to stop if you're driving 100?
160.
Did you say 160?
I say 5,650. 5,650.
Are you going to stick with your 80? Is that the final answer, Regis? You know with that? Okay. How many people are going to join Connor's Island and stop in 80 meters? You got loaded.
All right.
Okay. How many people think it's 160? Very popular, but that doesn't make it right. But it is right. How did you do that, Miguel? Exactly. Okay, because it says if you double your speed, the braking distance increases 4 times. So, yes, 160 is the correct answer. All right, you did. You're right. He's absolutely right. You guessed and you wanted to stick to your guns, which I admire, but sometimes you have to reevaluate and say, yeah, I don't know. I'll give you a chance of making it up, okay? All right, so now what if I'm not doing, what if I'm foolishly driving? This is if I'm going, hang on, let me just, if I'm going 50 kilometers an hour, it's 40 meters. If I'm going 100, it's, how much, Connor?
160.
160. What if I'm, like, being stupid and driving 150 kilometers an hour? Now, I said I'd give you a chance, but that's pretty hard, isn't it?
Well,
Wait. Well, how many times faster am I going? If I'm going 50 and then going to 150.
I'll just add 160 and 40. No, you know.
Miguel, what do you say? 320.
Yes. Live 220.
No.
Wait. Yeah, 300.
Okay, Miguel's going with 320.
I want 5,600 paper.
600. Okay, it's not the Price is Right, but
601.
yeah.
It's not 320. It's
Anybody else want?
Yeah, it's gonna be more
400?
something.
It's less than 320.
Yeah, it's less than
It's
320.
more than,
And it's under.
Okay, well,
it's gonna be
if
more.
I'm going 50 and then I go to 150, how many times faster am I going? Is it not 3 times? Am I not going 3 times faster?
Correct.
Right?
Well,
50, ignore the one in between. Is that not 3 times faster?
yeah.
50 times 3?
Yeah.
It's 200. I don't know, I'm just sharing that.
Okay, I know. Does it not say to square it? So I take 3 times and square it, which means 9 times farther. 9 times 40 is
360.
I was great. I multiplied it by 8.
300. Why would you do that?
I don't know. I'm doubling it by 4.
Yeah,
At least
it's
you
squaring.
See, at least I tried with the
Squaring. Okay, one more chance. What if I'm going 2.5 times faster?
Ah,
So what?
Same rule. What if I'm going 2.5 times faster?
Square 2.5?
2.5 squared,
Is 5.
And then times by 40.
and then multiply that by 40 exactly.
5 times 40.
It's actually 5.
Will I expect you to know that?
Yes. That goes
I
back.
got it. Wait, I can't see half my numbers.
Okay. Yeah. If it's 2.5 times, it's going to be 2.5 squared. 2.5 squared is? I think it's 9 something,
Nice.
isn't it? Oh no, yeah, it's 6.25, right? So 6.25 times 40. I can do this in my head. Watch me. 6 times 4 is 240, and a quarter of that 250.
Whoa!
Oh my god. Got it. What happened? I got
6.25 times 40.
You just blew everybody's mind.
Because I did a little bit of mental arithmetic.
Actually, no, it's that blows people's minds.
Quickly, because we don't have much time here. An inverse relationship means if one increases, the other decreases. Okay? For example, in a regular conversation, right, people would speak 50% of the time. You know who people are. Sometimes, if someone speaks more, then the other person has to speak less. Right? So that would be an inverse relationship. The more one person speaks, the less the other one gets to speak.
Understood.
That would be a good thing, yeah. Keep in mind in class. Okay, so I'm going to give you a little bit of time. There's 4 questions there. You can work with the person beside you. What time are we done?
323.
Actually,
Oh, we're on 22. Okay, so I will give you the answers to those tomorrow. Try those for me. I'll give you they're not easy. Try them. They're not easy. Try them. Try them right now. The 4 concept review questions.